So far, our perspective on vectors has been purely algebraic, but there's another geometric side to the story. So when we are working with vectors in R2, the idea is that we can visualize any vector as an arrow in the xy plane. So here's an example to illustrate the point. So here I'm working with my standard xy axes, representing R2, and here I've drawn some arrow in the xy plane. I'm calling this arrow V. Now, whenever you draw an arrow, the arrow starts at some point and terminates at some point. We call the place where the arrow starts at the tail of the vector, and we call the place where the arrow terminates the tip of the vector. So in this situation, our vector v emanates from the point 3, 1 and terminates at the point 8, 2. So you may be thinking, well, what does this have to do with the notion of vector that we've defined previously? Well, remember, a vector in R2 is a list of numbers. So where do we get that list from? We get the list from tail to tip displacement. So the notation I like to use here is this PQ with an arrow on top of it. This is signifying that this vector starts at P and terminates at Q. What we do here is we go coordinate to coordinate in the tip and the tail and subtract. So here the x-coordinate of the tip is 8, the x-coordinate of the tail is 3, 8 minus 3 equals 5. For the y-coordinates, the tip y-coordinate is 2, and the tail y-coordinate is 1, while 2 minus 1 equals 1. So the vector that we've represented here as an arrow in the xy plane has coordinates 5, 1. Now, the key thing to pay attention to here is that from our perspective, vectors are meant to represent displacement, not location. So we can do this tail to tip displacement arithmetic for any arrow, but one thing to notice is that when you do that arithmetic, you can get the same coordinates for a vector that's located in different positions. So here we have 4 vectors visualized here, v, w, x, and y. And if you did the tail to tip displacement arithmetic for each of these 4 vectors, you would find that they all have coordinates 2, 1. What this means is that these are all the same vector from our perspective, even though they're located in different positions. Okay, so once we have this geometric notion of vectors as arrows, we can start to prod at the theory from a geometric point of view. One thing that every arrow has is length. The notation we use to denote length is this double bar notation. And the formula says to sum the squares of the coordinates of the vector and then take a square root. Now, where does this formula come from? Well, let's look at an example here. So here we have our vector whose tail is 3, 1 and whose tip is 8, 2. Well, if we look at the x displacement here, remember that was the x coordinate, or the first coordinate, which is v1 equals 5. And if we looked at the y displacement, that was 2 minus 1, which equals 1. I don't know about you, but when I look at this figure, I can't help but think of right triangles, and the length of this vector would be the length of the hypotenuse of this triangle. Of course, that's given to us by the Pythagorean theorem. So if the legs here are 5 and 1, the length of this vector would be the square root of 5 squared plus 1 squared, which is the square root of 26. So ultimately it's the Pythagorean theorem that gives us our formula for length for vectors in R2. Okay, so that's vectors in R2. What about vectors in R3? Well, you may have seen before the x, y, z axes. This is how we visualize 3 dimensions. So with these 3 axes, I can locate positions with x, y, and now a third, what we call z coordinate. So here are 2 points in the x, y, z space. Here I'm starting with the point 1, negative 3, negative 1. Well, how did I locate this point in xyz space? The idea is that we travel 1 unit in the positive x direction, negative 3 units in the y direction, and then minus 1 unit in the z direction. So the idea is that we locate the point 1, negative 3 in the xy plane, and then for this point we drop down 1 coordinate. So that's the z direction. Similarly, over here we have a point Q. Here the coordinates are negative 2, 3, 1. How did we get here? Well, we traveled negative 2 units in the x direction, Then we traveled 3 units in the y direction, and then 1 unit, so that would be up, in the z direction. Once I know how to locate positions in XYZ space, I can draw arrows in XYZ space and measure tip to tail displacement. So if I wanted to figure out the coordinates of the vector v connecting this point P to this point Q, I can match all the coordinates of the tip and the tail together and then do my displacement arithmetic. So in the x direction, what's displacement? That would be -2 minus 1, that's -3. In the y direction, the tail to tip displacement would be 3 minus -3, that's equal to 6. And then now in the z direction, displacement is 1 minus -1, that's equal to 2. So the coordinates for this vector, which connects this point P to this point Q, are -3, 6, 2. Great. Now, there is a notion of length of vectors in R3, and the formula is similar to the formula in R2, except now we have to address the issue of the third coordinate. So our formula says that we now, to take the length of a vector in R3, sum the squares of all of the coordinates, and then put that result under a radical. So here I have my vector connecting our point P to our point Q. Remember the coordinates here were -3, 6, 2. So to calculate the length, we sum the squares of those 3 coordinates and then take a square root. In this case, we're calculating the square root of 49, which equals 7. So again, the point here is that the length of our vector measures the distance from the tail to the tip. Okay, now what if I wanted to think about vectors in Rn geometrically? Well, humans aren't very good about thinking about 4 and 5 and 6 dimensions visually. Nonetheless, we can still capture the geometry of vectors in those dimensions by being inspired by the geometry of lower dimensions. So if I wanted to think about a vector in R to the n, even if n is really large, visually, I just think of that vector as some arrow floating around in that high dimensional space. So when I'm working with high dimensional vectors, I will visualize them by just drawing some arrow and then imagining that that arrow lives in some large dimensional space. The key here is that the visible geometry of 3 dimensions that humans are good at working with defines geometry in higher dimensions. So it makes perfect sense now to talk about the length of a vector with lots of coordinates. If we follow our pattern that we've developed previously, the rule says sum the squares of all of your coordinates and then put that result under a radical. So in this case, let's say that I was studying this vector. The coordinates are 4, 0, -2, -5, -1. So this is a vector in R to the 5. There are 5 coordinates. How do I calculate the length of this vector? Well, remember my notation is this double bar notation. And what I'm supposed to do is just sum the squares of all of those coordinates and then take a square root. In this case, we're calculating the square root of 46 as the length. Now let's try to derive some properties of the theory that we've developed so far. One important property is this theorem, which tells us how scalar vector multiplication interacts with this notion of length. And this theorem is telling us that if I took the length of a vector v that's been scaled by a factor of c, that's the same thing as the original vector v's length scaled by the absolute value of this scalar c. And I want to walk you through the proof of this theorem to sort of acquaint you with this style of problem solving. If I want to justify that an equation works, the proper way to do it is to start on one side of the equation and then write valid equal signs until you hopefully get to the other side of the equation. So let's see how that plays out here. If I want to find the length of a vector that's been scaled by a factor of c, well, let's first say that perhaps the coordinates of this vector v can be labeled explicitly as v1, v2, all the way down to vn. So now I know the rule for scalar vector multiplication. The rule says that we scale every individual coordinate of our vector by this factor of c. So c times the vector is c times the first coordinate, c times the second coordinate, all the way down to c times the last coordinate. And so now I have a single vector that I'm taking the length of, and I can apply the length formula. Now I am summing the squares of all of the coordinates and then taking a square root. Well, the coordinates are the original v coordinates, each scaled by a factor of c. So the first term here is the quantity c times v1 squared. The second is c times v2 squared, so on and so forth. And remember how powers work. If I'm multiplying two scalars together and then taking that quantity to a power, the power distributes to those individual quantities. So what ends up happening here is that every term under this radical has a factor of c squared in it, and I can pull that c squared out. Now I'm multiplying the c squared times the sum of the squares of the coordinates of the original vector v, and I'm taking a square root. Well, remember, when I'm multiplying two quantities together and taking a square root, the square root sign distributes over those two quantities, which leaves me with the square root of c squared multiplied by the square root of the sum of the squares of the coordinates of the original vector. Now, here's where it's tempting to say something that's not quite right. I'm dealing with the square root of c squared here. It's tempting just to say, oh, well, that's just c. But remember, when you square your number, you forget about the sign of the original number. That quantity always becomes positive. So actually, when you take the square root of a square, that becomes the absolute value of the scalar. And of course, over here, we're left with the square root of the sum of the squares of the original coordinates of v. That is the length of our original vector v. So we have this sequence of equal signs that takes us from the first part of the equation we're trying to prove to ultimately the other side of the equation that we're wanting to prove. So that completes the proof here. Excellent. Now it's reasonable to ask, well, if I'm thinking of vectors as arrows, how do these operations that we've learned affect those arrows? The first one to address here is scalar vector multiplication. The idea, which comes from the theorem we just proved, is that when I scale a vector v by a scalar c, what we're doing is we are scaling the length of our vector, and the sign of the scalar we're using perhaps reorients the vector. Let's see what I mean with a visual example here. So let's say that I started with some vector v on the far left here. The idea is that if I multiply that vector by 2, what I'm doing is I'm taking that arrow and I'm stretching it by a factor of 2. On the other hand, if instead I were to multiply the original vector by a factor not of 2 but of 1/2, the idea now is that the vector shrinks in length. And here it would be shrinking by a factor of 1/2. Of course, I could have multiplied my vector by a negative number. So if I multiply by a negative number, it's the absolute value of that quantity that tells me how much I'm stretching or shrinking the arrow. And then the fact that I'm multiplying by a negative means that the arrow flips in direction. So ultimately, the idea here is that the magnitude of the scalar, which is the absolute value, controls the length after scaling, and the sign is controlling the direction. Of course, we also have this thing called vector addition that we learned. How does that play with our geometric interpretation? Well, here's the way to do it. Let's say that we start with two vectors, v and w, and we want to add them together from a visual perspective. Remember, from our perspective, arrows are meant to measure displacement, so they do not necessarily inherently have a location. So what we do is we form what's called a parallelogram. I'm going to draw my v and my w in such a way that they emanate from the same point, so that they have the same tail. Then I'm going to put another copy of my vector w, so that its tail is the tip of my original v. And I'm going to put another copy of my vector v in such a way that its tail is the original tip for the original w. So this gives me a parallelogram. And now the idea is that geometrically, the sum of these two vectors is the diagonal of this parallelogram. So if I were to start at the original tail for both of my vectors, I could traverse through v and then through w. That takes me to the tip of the addition of those two vectors. And one cool thing about this is that I could have gone through v and then w to get from tail to tip for this addition. But I also could have gone through w and then gone through v to give me that addition. Great. So this will actually bail us out of some interesting geometric situations that we'll encounter later in the course. So we might find ourselves in situations that look something like this. Maybe I have vectors that are known, x, v, and w here, but then in this diagram I have these other vectors that I don't necessarily know. I have this vector y that I don't know and this vector z that I don't know. Well, how can I figure out formulas for y and z in terms of these known quantities? Well, let's start with the vector y here. Y emanates from the original tip of x. So how do I get from tail to tip for y? Well, one direction one route that I could take here would be to go against this vector x and then with this vector v. Now the idea is that when I go against x, I am going with negative x. And then when I go through v, I'm adding v. So that's telling me that y here is the same thing as that vector v minus x. Let's play the same game with z down here. The tail of z is the original tail for w. And to get from tail to tip for z, an alternative route would be to go with w, so that's plus w, and then against this vector v, so that's minus v. So that's telling me that z here in this diagram is w minus v. Great. Okay, so let's build some more adjectives now that we have this geometric perspective on vectors. One important adjective for us will be this notion of unit vectors. Well, a unit vector is any vector whose length is 1. Here's an example of verifying whether or not a vector is a unit vector. This is the vector u in R4, and the coordinates are 1/2, -1/2, -1/2, 1/2. Well, how would I verify whether or not this is a unit vector? I calculate the length. The length is defined as the square root of the sum of the squares of the coordinates. But remember that we had this theorem that told us how scalar multiplication interacts with length. So one thing to notice here is that the vector we are dealing with is the same thing as the scalar 1/2, scaling the vector 1, -1, -1, 1. So I factored 1/2 out of the vector. So now I have a scalar 1/2 multiplied by another vector that I'm taking the length of. Well, how could I do this? My rule before says that's the same thing as the absolute value of the scalar, so that's the absolute value of 1/2, multiplied by the length of this other vector. Well, of course, the absolute value of 1/2 is just 1/2. And to calculate the length of this other vector, I sum the squares of all of those coordinates and take a square root. When I simplify my arithmetic here, I end up multiplying 1/2 times the square root of 4, which of course is 1/2 times 2, which is 1. So this vector is indeed a unit vector. Great. Now, another operation which will prove quite useful to us is the process of what's called normalization. The perspective here is that if we are using a vector to communicate a direction, well, perhaps I am communicating the same direction as you, but the vector I am using has a very long length, and the vector you are using has perhaps a slightly shorter length. We can normalize the conversation by looking at the single unit vector pointing in that direction. And the process of doing this, or arithmetically, is called normalization. So the notation I like to use here is this hat notation. So if I'm dealing with an original vector v, I'm defining the normalization as v hat here. And the formula says that I take my original v, and then I scale it by 1 over the length of v. So visually what I'm doing here is I'm correcting for the fact that my vector might be quite long, and I want it to be unit length. So if the original vector looks something like this, after I normalize, I don't change the direction of my arrow, but I potentially shrink the length if the length of v is longer than 1, or I'm actually stretching the length of v if the original length of v is less than 1. And of course, I keep referencing the fact here that normalization produces a unit vector. You don't have to trust me, though. You could prove it yourself. So if I took the length of the normalization, that's the length of the scalar 1 over the original length of v multiplied by v. Remember, I can factor out the absolute value of that scalar, so that's the absolute value of 1 over the length multiplied by the length. Of course, the absolute value is unnecessary here because 1 over the length itself is positive, and 1 over the original length times that length is indeed equal to 1. So normalization always produces a unit vector. Great. So here's an example illustrating the process. Here I have a vector in R4, 3, -8, 4, 2. The length of this vector is the square root of 93, so that's the square root of the sum of the squares of all of those coordinates. And then the normalization would be 1 over that length, so 1 over root 93, multiplied by my original vector. So the point here is that this algebra that we're developing allows us to speak geometrically about vectors. And this is a vector in R4, so that's living in some dimension that humans aren't quite equipped to fully comprehend visually. Nonetheless, this arithmetic allows me to talk about the geometry of R4. Okay, so this leads us to a new important concept which will follow us around throughout the rest for the rest of the semester. So we've discussed previously how to scale a vector, so you can take a vector and multiply by a scalar. We've discussed how to add vectors together, but we never developed a theory for multiplying vectors together. It turns out that there are lots of different ways to do this, but one of the most useful ways to do this is through what's called the inner product. So the idea is that if I have two vectors with the same number of coordinates, the inner product of those two vectors is defined with this angled bracket notation where the vectors are separated by a comma. And what this is telling me to do is match up all of the coordinates in the two vectors, multiply them, and then add everything together. People may have seen this before. Sometimes this is called the dot product of two vectors. I prefer the language and notation of inner products, but the dot product is exactly this operation. So we'll be using, and I expect you to use, the inner product notation, but this is the same thing as the dot product. So here's an example illustrating the point. Here I have two vectors, v and w. Both of these vectors are in R4, so it makes sense to take the inner product of these two vectors. Remember, mechanically what I'm told to do is match up the corresponding coordinates of my vectors, multiply, and then add everything together. So I'm multiplying 3 times -7, 1 times 0, 2 times 3, -2 times -9. Then I add everything together, and in this case, I produce the number 3. So evidently, when I take the inner product of two vectors, I produce a scalar quantity. Now, there's a word of warning here. Like with a lot of our operations, there are situations where you're not allowed to do the operation. And our stipulation for inner products is that the two vectors we're working with have to have exactly the same number of coordinates. So here I'm attempting to do something illegal. I can't take the inner product of a vector with 2 coordinates with a vector with 3 coordinates, and I can't take the inner product of a vector with 4 coordinates with a vector with more than 4 coordinates. So both of these are illegal expressions from our perspective. Okay, now that we have this thing called the inner product, let's survey some of the properties it obeys. One important property is the so-called commutative property. This means that it doesn't matter the order that I input the two vectors into my inner product. The inner product of v with w is the same as the inner product of w with v. There's also a left linear rule. So the idea is that if the first vector in my inner product is actually a linear combination of two vectors, so c1 times v1 plus c2 times v2, well, if I take an inner product of that linear combination with the vector w, it turns out that I can distribute the inner product across the linear combination in the first position. So this is the same thing as that first scalar c1 multiplied by the inner product of v1 with w, plus that second scalar c2 multiplied by the inner product of v2 with w. So that's the left linear rule. There's also a right linear rule. If the vector on the right-hand side of my inner product is a linear combination, I can distribute that inner product across that linear combination with this formula. There is one of my favorite rules. This is called the adjoint formula. So the idea is that when I multiply a matrix by a vector, I produce a vector. And there's nothing stopping me from taking that new vector and then taking an inner product with another vector. So there's actually a rule that says when I do that, that can be reinterpreted from the perspective of transposition. So the rule for the adjoint formula says the inner product of a times v with a vector w is always the same thing as the inner product of the original vector v with a transpose times w. We'll actually prove this later, but for now I just want to make sure that we're aware of this formula. The way I like to think of this is that if I have a matrix inside of an inner product, it can sort of teleport from side to side, but every time I move it from side to side, I have to take the transpose. And there's also a length formula. So if you think about it, there's nothing stopping us from taking the inner product of a vector with itself. Well, if I were to do that, the idea is that I'm matching up the coordinates of that vector with themselves and multiplying them together, which is the same thing as squaring those coordinates, and then I add everything up. That's the same thing as the process of taking length without the square root. So this tells us that the inner product of a vector with itself is always the square length of that vector. Okay, now, so this takes us to the question of, well, okay, I know what it means to take the inner product now of a vector with itself. The scalar that produces is meaningful. That's the square length of the original vector. But why would I want to take the inner product of two different vectors? What does that do for me? And there's a very satisfying answer to this question coming from the theory of trigonometry. So let's start with two vectors, v and w. I can take those two vectors and I can form a triangle with them. So draw them in such a way that they emanate from the same tail. If I look at this vector I've constructed here, this is v minus w. To get from the tip of w to the tip of v, I could go against w, so that's going with negative w, and then with this vector v, that's adding v. So the sort of other side of this triangle is the vector v minus w. Now, if I wanted to, I can calculate the square length of this vector v minus w. The square length of any vector is the inner product of that vector with itself. So what is the square length of v minus w? It's the inner product of v minus w with v minus w. Now, I can take advantage of my linearity properties. If I take advantage of the left linear property, I distribute the inner product over this linear combination, v minus w on the left. That leaves me with the inner product of v with v minus w minus the inner product of w with v minus w. And now, for those two inner products individually, I can use the right linear rule to distribute the inner product. This gives us 4 terms. So for this first inner product, I'm distributing across on the right. That leaves me with v inner product with v, then minus v inner product with w. And then I'm subtracting now the inner product of w with v, and then the inner product of w with negative w, so that would be minus a negative, that's plus, so that's the inner product of w with w. So now I have 4 inner products here, but I could actually clean this up a little bit. We know that the inner product of v with v is the length of v squared. The inner product of w with w is the length of w squared. And these two terms in the middle are actually the same by the commutative property. So this is minus 2 times the inner product of v with w. So that's one way to calculate the length of v minus w squared. This is using inner products. But there's another way to do this with a more ancient theory, and this is the so-called law of cosines. The law of cosines says the following. If I'm interested in the length of one side of a triangle, I can look at the angle at the opposite end and apply the law of cosines. The law of cosines says that the square length of that side is the same thing as the sum of the squares of the lengths of the other two legs of the triangle. So in this case, that would be the square length of v plus the square length of w. But then I need to subtract off what I like to call a corrective term, and that quantity is 2 times the product of those other two lengths times the cosine of the angle. So this is the famous law of cosines from trigonometry. And now, if I look at what we've accomplished here, we've calculated the square length of v minus w in 2 different ways. When I use inner products, I get this expression. Length of v squared plus length of w squared minus 2 times the inner product of v with w. But the law of cosines says that same quantity is the sum of the squares of the lengths of v and w minus 2 times the product of the lengths of v and w times the cosine of theta. Now, if I set those two quantities equal to each other, which is totally valid here, I end up with a nice relationship. The inner product of v with w turns out to always equal the product of the lengths of v and w with the cosine of the angle between those two vectors. So this is a famous and important theorem. The inner product of v with w is the product of the lengths of those two vectors times the cosine of the angle between those two vectors. So this is the answer to Well, why do I want to take inner products? The answer is inner products help us measure angles. There is a corollary to this. If I take the absolute value of both sides and acknowledge the fact that the absolute value of cosine is always between 0 and 1, I get the so-called Cauchy-Schwarz inequality, which says that the absolute value of the inner product of any two vectors is always less than or equal to the product of the two lengths of those two vectors. So here's an example illustrating the point. Here I have two vectors, 1, -3, 4, and the vector 1, 1, 1. Well, how can I calculate the angle between those two vectors? Well, I could start by calculating the cosine of the angle between those two vectors. Rearranging my previous formula says that the cosine of that angle is a quotient where the numerator is the inner product of my two vectors and the denominator is the product of the lengths of those two vectors. Well, this distills this angle calculation down to just an inner product calculation. When I do all of my arithmetic here, I end up taking the quotient of 2 as the numerator, and then the product of root 26 and root 3 in the denominator. So that's the cosine of the angle between those two vectors. Now, one thing to pay attention to is once we have this notion of angle, that enriches our vocabulary when talking about vectors. Angles are broadly categorized in 3 different ways, so we can view two vectors as being configured in broadly 3 different ways. One thing that's possible is that the angle between our two vectors is an acute angle, so that means it's less than pi over 2. This is exactly the situation where the cosine of the angle is positive, and therefore this can be detected by the inner product. Having an acute angle between two vectors is exactly the same thing as saying that the inner product of those two vectors is a positive number. Another possibility is that the angle between our two vectors is an obtuse angle. That means that the angle is larger than pi over 2. And this is exactly the situation where the cosine of that angle is negative, which is the same thing as saying that the inner product of those two vectors is negative. And of course, the only category missing here is maybe the most important category, and this is the situation where our two vectors form a right angle. A lot of people like to use the term perpendicular. Mathematicians really like the term orthogonal, so that's the term you'll find me using. So two vectors are orthogonal if the angle between them is equal to pi over 2. And you may remember from basic trig that cosine of pi over 2 is 0, which means that two vectors being orthogonal is exactly the situation where their inner product is equal to 0. So these are the 3 broad categories one finds themselves in when studying two vectors. Whoops. So for example, whoops, how did I lose my whoops. There we go. So here's a calculation where we verify whether or not two vectors are orthogonal. Here I have two vectors in R4. If I take their inner product, I end up producing 0. What does that tell me? That tells me that whatever R4 looks like, these two vectors are configured orthogonally. I'd like to now conclude this lecture by pointing something out regarding the theory of inner products. If I take a matrix vector product, what is going on here? If I take a matrix vector product, we've seen previously that the definition, and the most important thing to remember, is that in a matrix vector product, I am taking a linear combination of the columns of my matrix, where the weights in the linear combination come from the coordinates of my vector. Well, inner products allow us to put a different spin on that idea, or take a different perspective on that idea. So the idea is that if my matrix vector product is well defined, then if I view every row of my matrix as a vector abstractly, then it is legal to take the inner product of that row with the vector. And if I take the inner product of that row with my vector, that will produce the corresponding coordinate in the matrix vector product. So when I take this A and multiply by V, the first coordinate will always turn out to equal the inner product of the first row of A with the vector V. In this case, that's -7. The second coordinate is equal to the inner product of the second row with the vector in question, that's 8. Then the third coordinate is the inner product of the third row with the vector, that's -3. and the last coordinate is the inner product of the last row with the vector. In this case, that's 9. So generally, the ith coordinate of a matrix vector product is the inner product of the ith row of our matrix with the vector v in question. So this is something nice to remember, but never, ever, ever, ever forget that the real definition of matrix vector products is as a linear combination of the columns of our matrix, where the weights come from the coordinates of our vector. Before I let everyone go here, I just want to call attention to the Sage module posted on the course webpage. If you play around with the calculators here, you'll find that Sage has syntax for plotting vectors. So I've input a vector here, a vector in R2, and the syntax is v.plot, open close parentheses. And the Sage will produce a picture of that vector. Now, you'll notice that the default is to plot vectors so that they always emanate from the origin. You can actually move vectors around using this syntax. Inside the parentheses for plot, input start equals, and then the coordinates for wherever you want the tail of your vector to be. So here I'm defining a vector 1, 2, but I'm going to plot it so that it starts at the point -3, 1. I've also included some syntax here to change the color to green. So if I click evaluate here, this will plot my vector and it'll redraw the axes so that the tail of the vector is that point -3, 1. Now, if you want to, you could put multiple vectors in your figure. So here I've defined a calculator with 2 vectors, v and w, and then I've included syntax for plotting them together. So if you click evaluate, this will give you the triangle where I have 2 vectors and then the difference between them visualized. You'll also find here that there's syntax for calculating the length and also the normalization of a vector. The syntax for length is v.norm, open close parentheses, and the normalization is v.normalized, open close parentheses. So here I've predefined a vector in R4, and I've calculated both the length of our vector and its normalization. You'll find here that the length was square root 30, and then of course remember normalization is 1 over the length multiplied by the vector. Finally, there's syntax for inner products. Here the syntax is quite simple, just multiply the 2 vectors together with star notation. So here I've predefined 2 vectors in R4. To take their inner product, I simply use the star notation to calculate my inner product. So hopefully you find that